Perfect.
Should be seeing them now.
Shawn Dullen is a Systems Engineering Research Center Doctoral Fellow, currently pursuing his PhD in Systems Engineering at Stevens Institute of Technology. His current research interests are product development, set-based design, multidisciplinary optimization, optimal tolerance design under uncertainty, and Bayesian networks. Mr. Dullen works for the U.S. Army Combat Capabilities Development Command Armament Center, also known as CCDCAC, with 18 years of experience working different aspects of the DoD lifecycle as a quality engineer and systems engineer. He's currently the CCDCAC Key Parameter Development and Management Lead. Today, Shawn will be presenting his work, Quantitative Methods for Set-Based Design. Shawn, over to you.
Hey, good afternoon, everyone. I'm excited today to provide a good overview of the research I've been doing on quantitative methods for set-based design. I also will be plugging in the papers that I've already had published, so you can see them as the references at the back of this briefing. So the question is, why this research? Well, engineering and development rework is one of the leading causes for most program cost overruns and schedule delays. In order to develop a methodology to improve the way that we do at Armament Center implement product development, the underlying causes need to be understood and addressed. This led me to investigate the nature of engineering rework, which was my first published paper. Based on that research, the top causes were converging too early to a point-based design when there is uncertainty in the requirements and or performance. The second one is the exchange of uncertain and ambiguous information. So downstream activities are sensitive to preliminary information, and upstream activities are sensitive to downstream feedback, which even proliferates more when you have coupled activities where downstream is coupled with upstream activities, and they both feed each other, which could actually lead into what they call a churning effect, which never gets into convergence, significant rework over and over. And then the third area is in the misalignment of activities and organizational structure. IPTs are not structured to provide information in the same way that the system is relying on that information. Therefore, there's a lag and miscommunication of information, which leads into rework issues. So based on looking into methodologies that could address this, one that seemed to stand out more than the rest, and this is set-based design. It was identified by several other researchers and demonstrating its ability to address these rework concerns. So I investigated even further and started to research into set-based methodology and digital engineering implementation. And this led to the second paper, which I conducted a literature review and identified what is the methodologies out there and how was digital engineering being utilized to embrace and implement set-based design. And doing so, identified some gaps and opportunities for advancement. The one area I would like to highlight is the lack in understanding, implementation, and quantitative methods for defining, reasoning, and eliminating sets and utilizing that digital engineering environment to enable utilization of these methods. Here lies my research area. So you ask yourself, what is set-based design? Well, in set-based design, design engineers develop a set of design alternatives in parallel at different levels of abstraction. As the design progresses, they gradually narrow the prospective set of alternatives based on additional information from whether virtual prototyping, modeling, and simulation, or rapid prototype and physical, or the combination thereof, in which knowledge reuse and test data is utilized to finally converge to a final solution. So what does this sort of look at? Each design team defines their bounds, the set that they would like to work in which they map the design space. They explore their subsystem design space for all the possibilities and identify within their realm the feasible region. So each team does that, in which they end up communicating their sets of possibility through what is known as trade-off curves, limit curves, or other means of showing and displaying this information to other teams. The information gets combined and integrated to identify the intersection, right? This is the intersection. So when we look at this, this is the region in which we achieve mission level performance. So each team then communicates, and then we assess and identify based on achieving system level under constraining conditions. The teams will then improve their level of abstraction and improve their level of analysis to reduce the uncertainty in their estimation, in their performance, and reevaluate the designs. And then there's an iteration in which they establish feasibility before commitment and narrow down to a point-based design. So this is set-based design. There's still, as discussed, some limitations within the literature, which led me to dig into a comprehensive literature on quantitative methods. This literature review was based on trying to address 6 fundamental research questions. The first one is, what formal quantitative methods were used to define and reason about sets? How was the research evolved for each of the quantitative methods, and what gaps currently exist? What are the strengths, limitations, and of these quantitative methods? The fourth was, what formal methods were used to delay decisions so that uncertainty could be reduced prior to final design convergence? The fifth, the evaluation methods were used to narrow the design space, and how is the level of analysis being gradually improved? So these 6 fundamental questions still need to be addressed to understand what quantitative methods can and cannot do for set-based design. The way I went about that is based on this schematic right here, is we looked at, does it exhibit set-based concurrent engineering based on the previous chart that's sort of laying out the principles for set-based design concurrent engineering. Also looked at what is known as set-based thinking, which is based on considering sets of distinct alternatives concurrently and delaying convergent decisions. If it went through that, then I looked at, was they quantitative or qualitative, and looked at what metrics were utilized and how they increased the level of detail. Hundreds of papers were evaluated, in which I narrowed down to about 120 papers to address these 6 fundamental questions. The bottom line, I identify papers not traditionally considered set-based design and address these fundamental questions. So what were the fundamental quantitative methods? Well, here's the formal list of quantitative methods that were used to solve set-based design problems. The methods checked were the ones for further consideration. And the reason why is the researchers provided explicit detail on how they were actually using these methods to implement set-based design, but they also advanced the methodology specifically to provide in the application of set-based design. So it wasn't just taking textbook multi-attribute value theory or fuzzy logic. They've altered it in a way to implement set-based design, whereas the Topis and HP did not. There was little detail, so they got removed. So these 6 formal methods were evaluated in detail. So here's the list of strengths and limitations. Notice that some of these methods are interval-based. They have trouble handling design spaces that are irregularly shaped and discontinuous, such as constraint satisfaction methods, fuzzy logic systems, multi-objective optimization. But methods such as Bayesian network classifiers can handle these type of situations. They can handle discontinuous spaces. They can also handle limited data, mixed data, and incomplete data. So for more information on quantitative methods and the answers to those 6 fundamental questions, please read my survey paper on set-based design quantitative method that is published in the Systems Engineering Journal. You can see the reference in the back of this briefing. But now where I want to go in is there's a lot of gaps that I identified in opportunities, but what gaps do I want to fill in and provide you some more detail? So some understandings that was limited is hybridization of these methods. How can they be hybridized in a way to better implement set-based design? How are we mapping the design space? None of these papers really got into the differences in mapping the design space, and does it matter? And this is a thread that I'm going to pull further throughout this briefing is mapping the design space. So let's look at how technology is developed and how systems are developed. And the reason I want to bring this in is within the literature, one perspective that was not considered or really emphasize is the way that we develop technologies and the way that we develop systems. At the top is the mapping of technology maturation to the acquisition lifecycle, right? Notice that early research begins at the component level. So we're starting at the bottom, in which we start maturing this technology to subsystems and et cetera, right? The technology readiness level improves as the technology gets integrated into the next system. So in here, we look at basic research. For us, we would be looking at ARL to provide that, or academia. Then within our systems at Armament Center, I'd be looking at how to start looking at indirect or direct fire, and I start maturing that science, and I'm building it from the bottom up, creating knowledge. There's knowledge at each of the areas that can be utilized at the next layer. So the question is what quantitative methods best facilitate bottom-up approach? Also, as systems engineers, we know we take a top-down approach, and this is what's really laid out at the bottom. As we start to go through the acquisition process, the technology maturation risk reduction phase, we're starting from the top down, right? We're implementing this V, and then we iterate that as we go through each stage of the life cycle, but we start from top down. So the question here is, does different quantitative methods align better to a bottom-up or top-down design? Can we hybridize the top-down and bottom-up methods to improve our ability to implement set-based design? And how can we utilize the improvements in the digital engineering environment to better enable the hybridization of these methods? These are the questions that still are lingering, that still need to be addressed. Another area I'd like to point out is in regards to the generation of design alternatives. One popular approach from taking a top-down approach is the utilization of what is known as a morphological box to create design instances. Each column represents a logical element. So for this example, a toy projectile launcher, say catapult launcher, we have identified behavior and the logical elements to perform that behavior, in which for each one we brainstorm physical solutions for that element, in which we string together the technologies and figure out ways to integrate and design a system in which we end up parameterizing now that system in evaluating the trade-off criteria. So we bring it together and evaluate how well it meets mission performance. The question here is, these alternatives, should the team spend a lot of time integrating and parameterizing these physical solutions that can even achieve these threshold objectives? Can visualization techniques of the design space enhance one's ability to even generate these design alternatives? And does the way we map the design space influence the way that we even generate design alternatives? These are another set of questions that need to be addressed. Now, looking at this, excuse me, sorry, I'm taking a drink. Now, taking these considerations into effect, I believe these concepts can provide a paradigm shift to the way that we implement set-based design. And what do I mean is, the current approach, the design teams create set of alternatives that may or may not achieve mission level performance. And then they communicate their sets, right? So we're creating here the design possibilities. Then we're communicating those. They may or may not, and there's some iteration in here until we can identify a section of intersection here, in which then we start to improve the level of detail and analysis in which we establish feasibility and move forward. But what if we give the design engineers a better starting point? What if we utilize backward mapping, in which I already define a set of system criteria and subsystem trade space that achieves mission level performance prior to even generating these alternatives, which is known as backward mapping. So if I can provide this and give each design team their region, and then they go in and start looking at different ways of looking at the data to generate more efficient utilization of design alternatives, and then use forward mapping to see how well they achieve performance, can I integrate, hybridize the best of both worlds to achieve where we want to go, to reduce the number of iterations required to establish feasibility? And then I'm focused in on how I'm lowering uncertainty into my stakeholder needs, the criteria, or is there emerging threat Do I have a pulse on that? And how can I reduce the uncertainty in the information I'm used to narrow down the set? I believe that hybridizing and bringing them together and utilizing a digital engineering environment could get us there. So you ask, well, what is forward mapping versus backward mapping? Well, let's look at to the left. So if we take a bottoms-up approach, which a forward mapping aligns a little bit better to, we're defining at that lower level, what are my design features, right, at the component, right, that basic research. So when I have those, so basically I define my input variable and I solve my output. And essentially I'm propagating that at each layer, right? I define what my design features are, solving for my subsystem level attributes, which are now inputs to my system level. And I just propagate and evaluate, get feedback, and get a loop for iteration in a bottom-up approach. But if you look at backward mapping, this aligns a little bit better from a top-down. Why do I say that? Because we define our mission level attributes, right? What is our threshold and objective? What is that range set? And solve now. That's my output that I want. Now I'm going to solve for a range, a set of system level attributes, and then I solve for my subsystem. So I'm backward mapping the design space. A lot of people are familiar with the forward mapping, but let's just talk a little bit about an example of this backward mapping and what do you mean, Shawn, in regards to this? Well, let's just take a very simple two objective trade space, right, for visualization purposes. So I'm looking at, I established my threshold on an objective, or I went out to the stakeholders and identify what are my walkaway points, right? What is the minimum of value and performance that you're willing to pay? Anything less than that, you're not willing to consider, which sometimes is even less than the threshold, right? For people who've done a lot of stakeholder needs. So I define that, right? Now I understand the range in values that I can do to obtain mission level performance. So what I'm gonna do now, this is my feasible region, is identify what value my input needs to achieve that, right? So now I have my performance, and now I'm gonna go and identify all the range and values, the feasible region for W1 and W2, and identify that feasible region of system level attributes. Now this is the trade space. Anywhere within this red region, if I forward propagate that value, will fall in the feasible region for meeting my mission level attributes. In doing so, I can just backward map again here and identify what that value is for the subsystem, and et cetera. So any value that falls within the constraints will achieve mission level performance, because if I forward propagate, it will fall somewhere in here, and I do it again, it'll fall within this region. So backward mapping with forward mapping provides a good way of understanding the trade space earlier on to enable some efficiencies there. So this is where I'm looking at, is hybridizing these approaches. So you ask yourself, well, what are some of the methodologies that could be utilized to help with backward mapping? Well, that's a good question. Well, Bayesian network classifiers are a special type of Bayesian network designed for classification problems. Bayesian networks are probabilistic models that represent a factored joint probability distribution as a directed acyclic graph known as a DAG. And really that's the structure right here that I'm talking about, right? The vertices represent random variables, and the edges represent direct connections between them and each of the variables in a conditionally independent of its non-descendants, given the state of the parent vertex. So really what we're looking at is first learning what the structure is, right, of classifying. And the simplest case is what they call naive Bayes, independent, right? So I just define X1, X2, X3, X4, and each of them are almost like main effects, if you're familiar with design inference, right? I change them and I can get the classification. Over here is fully independent, fully dependent, right? There's interactions associated to this structure, and then things in between. So we learn that. Then after we learn the structure, we want to learn the parameters. And we can do this from discrete cases or a continuous case for the variable. The discrete case, we're looking at probabilities associated, and then we use, for continuous, we use a kernel density function to come up with it. So once we understand the structure, and then we learn the parameters, we can classify whether it's feasible or non-feasible or infeasible. And the way that this is done is by applying Bayes' rule here for classifying. in which we compute the probability of classification given the specific instant, right? The input variables, what's x1, x2, x3, etc. And then we predict the class with the highest posterior probability using this formula. So if it's, we set the threshold, so what's the probability above 50% as it fallen in? It's either feasible or not, and we can adjust that. So that's how we do classification. So this is a predominant method within classification methods, and this is the method that was utilized within the set-based literature, and there's some improvements can be made in there. The next method is something that was not in the set-based design literature, but could provide a significant value in the way that we're classifying, especially in nonlinear regions, which is known as a support vector machine classifier. And is defined as a boundary between two classes by maximal separation of the closest point. The separation of the two classes is accomplished by developing a linear decision boundary by using a separating hyperplane. So what we're doing is trying to create a separation. Anything that's on one side of this hyperplane would be classified in a certain way, and anything on the other side would be classified. So in this case, we would say this is feasible and say this is non-feasible, or vice versa, right? It's a two-class problem. But we bring in the next thing for what makes support vector optimization here is the optimal separating hyperplane, which is the linear decision function, which lies between two supporting hyperplanes that separate the two classes of data by maximal margin. Wow, you said a lot. So really all it is for each of the data points, I'm going to create a supporting hyperplane on it. And I have these support vectors. So what I end up doing is for each one, using these two support hyperplanes, and I'm going to be calculating this optimal hyperplane right here. And what I'm doing is trying to maximize the distance from this plane and the support hyperplanes. And then in doing so, I'm going to go all the way through the data and identify what is the optimal one, what maximizes it, and I'm going to use that to classify the design space. So this is what is known as a hard margin. Anything on this side gets classified here. Nothing falls within this transition region within the margin. All right, so not necessarily realistic. What is more realistic is something that is not fully linearly separable. And then in this case is typically when there's noise in the data or some error in the data. And the way that we handle this is by including what is known as a slack variable. And then by including the slack variable, we go through a very similar process in calculating out our hyperplanes and then maximizing this marginal distance and determining our support vectors in that and then making our decision on it. And essentially, it falls within two, the soft margin and the hard margin. So anything that falls outside of here, we pretty much are evaluating very similar here. It's in this class or that. The tricky region is the things that fall in it, and that's where we use the slack variable in there in the calculation to determine the classification for the things that fall within this region. So that gets into the linear case, and you might be saying, well, Shawn, all right, this is good, but what happens if you do something that is nonlinear? Well, that's the beauty with support vectors. They can handle nonlinear separable data. And the way that they do that is using something called a kernel function. People are familiar with, say, polynomial functions in regards to that, radio basis functions. And really what it is doing is increasing the dimensionality of the data in a way that stretches it in a multi-dimension to create a condition where the information can be separated by a hyperplane, very similar to the 2D case. So what I mean is, say if I had x1, x2, and it was nonlinear, say almost like a circle on there in the center where most of the data felt feasible and anything outside of that was infeasible. What I end up doing is creating a third dimension, a higher dimension, stretch the data, see if I can create a support vector. Then I would add a fourth dimension, fifth dimension, sixth dimension. So eventually I could just stretch this data in a way and create this hyperplane in doing so. So it has a very good utility, and the hyperplane is always one dimension less than the data that you're looking at, as you can see here. In this two-dimension case, right, I got a line, right, so it's one dimension less. So anyways, this is another really promising area, is the utilization of support vectors to gain that with the limited data, because we're only reliant on these vectors, these data points. We're not taking in all the data into consideration. So efficiencies in running and evaluation. So there's some good utilization there. So you ask yourself, well, all right, this is good. So what are the next steps forward? Well, what I plan on doing is comparing and contrasting the forward and backward design space mapping methods. The methods will be evaluated based on how they influence the generation of design alternatives, how effective they are in defining sets, reasoning about them, and eliminating the sets. And based on the results, I plan on hybridizing the approach so that we can will be developed in a way that I can implement an armament center case study with the aim of reducing the number of design iterations required to determine feasibility before commitment. And in there, then I start looking at ways of reducing the uncertainty into stakeholder needs, which would be having a better pulse in regards to threats, emergent threats, changing threats, the likelihood that the stakeholder criteria or mission level performance is going to change, and better ways of reducing the uncertainty within modeling and simulation and test and evaluation, things of that. And then I would converge into a point-based design. That's where I plan on moving forward. That gives you an overview of the research. Is there any questions?
And Shawn, can you see the questions on the side?
I'm going to pull it up right here. Are you doing Q&A or just everyone's in the chat session?
In the chat.
In the chat. It's starting with Christopher Hoffman, going back to slide 3. Do you see that?
What time is that at? I'm looking right there. All right, Chris. The set-based design subsystem boundaries in slide 3 don't select the design space expansion that also happens. How did your research approach considering set expansion? So for us, within there, we have the system level sets, and then looking at the sets of design alternatives at the subsystem, right? So we could have a variety of different instances in regards to that. So for the way that we're considering it as a unique set of combinations, and then you're going to have a unique set of parameterization for that system level design alternative. So that's the way we're creating unique sets at system and subsystem level. I'm not necessarily sure where you're going beyond that for set expansion. Over. And we could follow up more offline to get in that too if you want to call me. The next question is that Beth Wilson.
Yes, but this is actually, I'm not sure, Shawn, if you were joining the tutorial this morning, so it actually ties back to the tutorial and the team that was working on that. But she asked, you know, as a form of set-based design, do they see potential connections there? So I'm not sure if you joined that and can answer that question.
No, I'm sorry, Beth. I was not able to attend that. I'll have to look at that and
I can
look at that.
I can offer an answer, Shawn. And so because this CSRM loop she talks about is a functional modeling approach, it defines sets of functions in the space, and you can down select those to critical functions based on preferences in the space and sets of critical functions even. The problem you'll have at the functional level is parameterizing those functions. And so the quantitative approaches won't apply very well, but on the other hand, the approaches like AHP or TOPSIS might apply pretty well in those spaces in terms of quantifying your decision space as opposed to quantifying or parameterizing it. So that might be the answer, but you know, we haven't necessarily looked at it in this context. So hopefully that answered the question. There's another question there for you, Shawn.
Yeah, so for classification, you can think of it as providing a whole range. Almost, a lot of people say, is how much variation I can have in an input to achieve that, say, mission level performance that I'm going in. So it almost encapsulates the entire set of possibilities needed to attain that. running multi-objective optimization when you're running through and you're looking at your Pareto function, you're not necessarily capturing, right? That's a forward way of going. I'm changing instances in there, identifying and optimizing within that realm. There are some cases within multi-objective optimization, like Gray Wolf Optimizer, where they're starting to look at it, or interval-based multi-objective optimization, taking that forward approach and creating a whole set instance. But what happens now when you look at that and introduce uncertainty associated to your modeling and simulation, especially on the early stage, and start adding new levels of abstraction to that. So within the optimization approach, for at least in the cases that I was looking at, I started off with MATLAB models, and then I went into 3D SimCenter models for kinematics, say for the toy catapult and FEA analysis using Abacus, and ran through optimization techniques on there and identified a set of alternatives. And then I compared that with taking the backward mapping, and I was able to have more design instances to achieve performance as I started to increase the level of fidelity of my modeling and simulation than if I went with multi-objective optimization. So anyways, that was just some of the preliminary research as I started to evaluate. That's still unpublished. It's going to be in a paper, hopefully. I'll be done during this winter, the December, January timeframe, and hopefully you guys will be able to see that. But that's some of the things that I got from initial preliminary understanding and comparing and contrasting some of these methods. But I haven't went through everything yet between them, and still working on that now. Over.
Great. Thanks so much, Shawn.